Let me say now that we have another president speaking on a technical subject. Mr. Everett from the Miter Corporation is going to tell us about Whirlwind.
Thank you. Well, first I'd like to apologize for being here instead of Jay Forrester. Jay, as I'm sure you're aware, was the leading spirit in more ways than one in the digital computer laboratory. And he's sorry he can't be here, and I guess you'll have to make do with me. Secondly, I wonder why I'm here at all, because several of the previous speakers have acted as if MIT never built a computer. I assure Dr. Booth that if he had come to see the people who were working on the computer in 1946, he would have found us there and welcomed him. But he didn't. He went to see Sam Caldwell, and I won't go into that. Thirdly, when I started to prepare this speech, I wasn't quite sure what was wanted in the way of computer history. And as far as I can tell from listening to the historians, I probably have missed the boat. I have something that I think would technically be called, first of all, a chronology, and secondly, a memoir. But I'll leave that up to you. Whirlwind is a kind of a special machine. That is, it was designed by engineers for engineering purposes, and in particular for the control of real-time devices. It's rather different than being motivated by the desire to do mathematics or to solve equations or to carry on various and sundry other things, many of which Whirlwind eventually did because computers tend to do a lot of things. But it was really not the motivation for the machine. The early history of the computer, in fact, stemmed from this view. It began as an analog computer. In 1944, the group under Forrester was at the Servo Mechanisms Laboratory, which is led by Gordon Brown. And we began work on something that was called the Airplane Stability Control Analyzer, which was a device which had been conceived by the Special Devices Center of the Navy, which was run by Louis de Flores, and which had built a number of aircraft trainers. And the idea was that one could build a generalized trainer, and one could set up this was one that actually solved the equations of motion and the aerodynamic equations. One could then put wind tunnel data into it and end up with a trainer which would fly like an airplane that had not been built. This involved building a cockpit and building a very large computer. And we started out to build an analog machine. And we worked at that for some time. The problems were basically the speed of operation, the amount of equipment, and the dynamic range that was called for to solve this particular problem. Nowadays, you can go down and buy things like that. In those days, you could not. We worked on it very hard, and I think if we had been forced to stick with it, we would probably have built something that would have served a useful purpose. However, in 1945, Jay began looking at the new digital computers, talked to a number of people, went to a computer conference, and as I recall it, late in 1945, he came back and said, we're no longer building an analog computer, we're building a digital computer. Now, things were different in those days. We didn't have a big study group. He said, we're building a digital computer. We all thought that was great. He achieved the support of MIT and the Special Devices Center and so on, which were really also a bunch of engineers. And we began the process of building a digital computer in late 45. Now, at that time, the concept of such a machine, of course, was well understood. I think that's been clear. And the general ideas, the philosophy of it, and so on was available. ENIAC was there, and it proved you could make a large machine and make it work. There were EDVAC ideas on paper. And perhaps most important, but seldom mentioned, the radar technology, which was coming out of the World War II activities, in tubes and pulse circuits and storage devices which have been developed for moving target indicators and so on. It was that technology foundation that made it possible to build digital computers, electronic ones. It was just sort of barely possible, however, There was a limited amount of test equipment. There were a limited number of devices and components. To use a perhaps dubious word, there was no real technical infrastructure as we know it today. There were few instruments. We had to go ahead and do almost everything for the first time. And when I say we, I mean not only the Digital Computer Laboratory, I mean all the people in the computer business. Tube life characteristics were unknown. Now, the MIT group had a particular problem. And that is, we were still after the airplane stability control analyzer, which represented a class of problems that had to work in real time. And this required, first of all, that the machine have enough capacity, speed, storage capacity, and so on, so that it could keep up with real time. You couldn't say, well, I didn't quite make it, I'll run a little bit slower than real time, because there were people in the loop. And secondly, the downtime had to be kept very low because of all the people and other things that were associated with the machine. So failures were very expensive and troublesome. So this drive for speed and this drive for reliability, in order to make a real-time machine, these were the driving forces on the Whirlwind group. We began by looking at a 3-address serial type machine using what would nowadays be called a read-only memory, supposedly based on cathode ray tubes with punch cards in front of them, and a storage tube memory. We laid out the diagrams for such a machine and did some circuit work and did some work on the memory devices. And in the summer of 46, at about the same time that the Moore School was running its famous course, we wrote a program for how we would solve the airplane stability control analyzer job using this machine. It had about 2,000 instructions in it. Thank goodness we never had to check it out. But it showed us that the machine was marginal as best we could see, and also we were having quite a lot of trouble, particularly with the storage. And we decided to go for a parallel type machine. It was faster and it was more flexible, at least for our applications. We further decided to build a small machine first. In serial type machines, you can change the word length, and that sort of changes the speed. In parallel type machine, you change the word length and it changes the size and therefore the cost. And therefore, we decided to build a smaller machine, and as some other people have said earlier, we expected at a later occasion, or a later time, to build a larger machine, which would hopefully better do that job. We selected a word length of 16 bits. Now, that's a nice binary number, but that wasn't how it came about. It was determined by saying, what's the shortest single address instruction that looks reasonable? Our analysis of the programs we were interested in showed that 1,000 words was tight and 2,000 words was considerably better. That gave us 11 bits. And we said we knew we needed at least 16 instructions, and 32 sounded reasonable, and that's 5 bits. And therefore, the 16 is not a binary number, it's the sum of 2 primes. Now, we were quite well aware, of course, that this was a short word length, and people were very worried about round-off errors and so on, as has been mentioned. And we expected that a great deal of the work would be done with double or perhaps triple precision, which would slow the machine down. But at the same time, there's a great deal of overhead that goes on, and that could go on in the 16-bit length. It turns out it was really a better choice than we expected. Somebody mentioned that, I think it was yesterday, that Johnny von Neumann had made a remark to Jay Stratton, I think it was, about how Whirlwind had such a short word length that he was concerned about its ability to do anything useful. I think Johnny did understand why we did it, but I think he was concerned about the word length rather more than we were, because he tended to think of different kinds of problems. And I think Jay Stratton understood what we were about. By 1947, the logical design of Whirlwind had been completed, and it was issued in a 2-volume report. The memory was to be specially designed storage tubes, and the machine was to include a test memory of 32 registers of flip-flops, of toggle switches, and 5 registers of flip-flops, which could be inserted anywhere one chose in the 5, in amongst the toggle switches. The organization was relatively straightforward. A couple of days ago, I would have said it was a von Neumann type machine. I'm no longer so sure, but If you look at the block diagram on sort of one page, you'll see that it's got a storage device and a calculating device and the control and input-output. So from that point of view, it is, and it's a stored program machine. But once you get, of course, more deeply into it, you'll find that it deviates quite a bit. It had a main bus and a repeat back system for checking transfers, and it had a very flexible control to permit the addition and perhaps modification of instructions. Now I'd like the first slide, if I may. This is a picture of the BARDA building where Whirlwind was built. I'm particularly glad I brought this for Professor Burkhoff. It is in Cambridge, Massachusetts, that is. It is on filled land at the south end of town, very close to a large trade school, which was built in that area. The Whirlwind occupied about 1/3 of the top floor when it was first built, and subsequently, when it was used for air defense and so on purposes, about 1/3 of the building filled up with miscellaneous things that were attached to the machine. Now, we were working on standards, pulse shapes, standard circuits, voltages, connectors, tubes, and all the other things that one has to worry about. We were particularly concerned, of course, about vacuum tube reliability. Tube life was largely unknown in those days. We expected a lot of tubes, and we expected a lot of trouble with them. Failures of tubes, as you know, are generally of three kinds. There was a kind of infant mortality, and you could get rid of that by pre-burning all the tubes, which we did. There were mechanical problems, which were treated by careful design and construction. And in fact, we used special tubes. We got a lot of cooperation from the tube companies, and we paid $5 or $10 a tube, which was a lot of money for a tube in those days, and kept out a lot of the mechanical troubles. But also, there was a problem of gradual decay as the tubes aged for various reasons. The emission would go down from the cathode. We found some tubes build up interfaces. There were a whole set of problems of this sort. And Jay decided that we should put in a system which was called marginal checking. All the circuits, of course, were designed with safety margins, but as the tubes aged, these margins would get less and less. So if while the machine is running, you change some of the voltages, in particular the screen voltages were often used, you could move the operating point within the margin, and you could measure how large the margin was. And if the margin got too small, then you could replace the tube then, instead of waiting for it to go out on you in a very inconvenient time. Next chart. This is a picture of the 5-digit multiplier, which we built in 1947 to check out the circuitry and this particular idea. The young man with the saddle shoes is Norman Taylor. The machine multiplied two 5-digit binary digit numbers together and checked the result, and kept that up day after day. And it underwent marginal checking and preventive maintenance at reasonable intervals, starting out every day and subsequently less often. Had about 400 vacuum tubes in it. And it used to run normally for a few weeks. It once ran for 45 days. Now, we knew all these people that you've been talked about before. One of the nice things about the computer business in the early days, it was fairly small. Everybody knew everybody else. Everybody talked to each other. As far as I know, we all knew what each other was doing. I don't think, however, that the reason that we all did things differently was because, we wanted to do it our own way. Certainly, we were willing to buy anything from anybody if we could trust him. But we didn't trust anybody, and neither did anybody else. Anyway, Howard Aiken came to see us, and we took him up and showed him this. And Jay was very proud of it and told him how it had run for 45 days and had done 10 to the 10th multiplications or something, and it hadn't made a mistake. And Howard looked at it, and as he was going out the door, he said, 5 bits, that's about 1 digit. He says, trouble goes if it's the square of the number of digits. Say 10 digits, let's factor 100, that's about a half a day. He says, that's not bad, and off he goes. Now, the machine was arranged in sections we built it this way. The machine was arranged in sections so that you could decide what excursions you wanted in the various sections, and it also helped in the checkout. Next slide, please. This is the control, the marginal checking control on the main control panel. You could dial up one of the sections there and set it if you wanted to by hand, but it could also be set automatically. Next. This is a picture of the marginal checking operation. That's a crossbar switch. And these are all the relays that did all the things to the machine. And then the machine ran check problems of one sort and another. And this was done once a day. It took about 15 minutes to go through the machine. Now, in general, the results of this, I think, were very good. We found that after we made some changes in them and learned how to live with them and so on, that vacuum tubes are really pretty good. Now, the next one, please. This is an old chart dating from 1950 of experience with Whirlwind as of that time. Had 3,500 tubes, and that's the loss rate. That was an undetected decay rate of about 1/10% per 1,000 hours. Tube life was generally a few percent per 1,000 hours replacement rate for poor tubes. Those were the poorest ones we were willing to use or had to use. And of the order of 0.5% per 1,000 hours for some of the better tubes. Now, in the process of building a machine, we found we had lots of trouble. And one of them was that when we once went around the building, we found everybody was working on test equipment. Nobody was working on the computer at all. Next one, please. This is not very virulent example, really. That's an eight-position diode switch, which is on top of this synchroscope. And we found we had to do something or we'd never get the machine built. So we decided to undertake the development of a set of digital building blocks, including clocks, counters, gates, flip-flops, pulse standardizers, etc., with standardized power supplies, all designed so that they could be plugged together to generate any particular sequence of gates and pulses that you wanted. And then we would build these in a large enough quantity so that if somebody wanted some test equipment, he could have it, and he could go back to working on the machine. The next one is an example of one item. That's the clock pulse generator. This really worked very well. Two of the engineers at Whirlwind, George Hoberg and Harry Kanosian, left and went to Burroughs, where Harry designed a line of test equipment of this sort, which was marketed by Burroughs. And George Hoberg actually built a whole computer out of this stuff, and it really worked very well, although it was a sort of a large collection of things. We also undertook a training program. Next one, please. We had to train everybody for everything, including we had standard soldering. If you hadn't been through the soldering course, you weren't allowed to solder anything. I never went through the soldering course, and by George, they wouldn't let me solder anything either. This is a course on the logical structure of the machine, and I won't point them out, but there are some of the old timers of the Digital Computer Lab scattered around amongst that group. In addition to this training, there was firm control over all aspects of the design and the construction. There were good records, careful drawings, careful design control, standards. The whole thing was done as a very carefully engineered and maintained operation. It being our feeling that if the thing ever got away from us, we'd never catch up with it. Next one, please. We also decided to build a machine in a two-dimensional array. That is, this is one digit of the accumulator, and everything is spread out two-dimensionally, and you can get at any piece of it in case you want to measure something or fix something or something of that sort. So all parts were available at all times. And next, please. This is a picture of the room in which Whirlwind was eventually assembled. After it was up, it was very hard to take a picture of it. This shows the racks going up. Each one of these columns represents one sort of, this particular section here is the arithmetic element about to go up. 8 digits are on this side of the aisle and 8 digits are on this side of the aisle. Next, please. We're beginning to make progress. People are screwing things in here. Next, please. These are the cable trays up above. Next, please. And here are the panels going in. That's the other side of an accumulator. This is a filament transformer. These were scattered throughout and were adjustable in voltage so that we get optimum voltage on things. Next, please. That's the right half of the arithmetic element. These are the 8 columns, and these are various drivers and so on. Next, please. This is the test storage that I mentioned, the back side of the 32 registers of toggle switches. This worked very well, enabled us to check out the machine and subsequently to check out the memory, and then proved of continuing value in that we used it for the purpose that Morris Wilks mentioned this morning. You had to be able to get the machine started, and the input routine was in there. There were 32 by 16 plus 5. The other 5 switches should tell you where to put the flip-flops. By the way, the 5 flip-flop registers could be put in place of any of these 5 registers. And then the toggle switches gave the initial conditions for the flip-flops. And that's 517 switches, if my memory serves me. And one of the peculiarities was that nobody that I ever knew of was ever able to set all 517 of those switches right the first time. Now, we had thought about that and it made it a little harder because, you see, the machine, this is the sine side, the high side, and then it moves down to the right. But the switches are on the other side, so of course the sine is on the right and the thing is backwards. That was just to make it a little harder. Point of fact, we didn't know that we did that until the first time we set it up, and then we said, my God, but it's too late to fix that. Next, please. This is the central control that I mentioned. This is the 32-position switch that selected which instruction you wanted. That set up one of these horizontal lines. And there were vertical lines which went to amplify gate tubes down here. You picked up which time pulse you wanted, so that you could get any sequence of pulses. Next, please. This is a close-up. It's not a very good shot, but it's a close-up of the matrix itself. And by soldering in these diodes, you could change the thing or put in different instructions. That's Norm Taylor again. That's Gus O'Brien. Believe it or not, that's me. Now, there's another peculiarity of Whirlwind. It was desirable to couple the gate tubes through capacitors to the flip-flops. The capacitors don't pass DC, and this was a machine which ran at any speed you wanted, including step-by-step. And to keep things working properly, you had to make the flip-flops then turn over at fairly frequent intervals, and you couldn't count on that. But we noticed, however, that the information of the content of the machine would not be lost if you turned over all the flip-flops. And this, in fact, happened. It was set up in what were called restorer pulses, and approximately every 20 microseconds, the whole machine would stop what it was doing. All the flip-flops would turn over, and all would turn back. I would reset all of the capacitors and make all the gate tubes work. Well, it turned out this worked, but it really wasn't one of our better ideas. And before long, we went to DC-coupled gates, and we're happier that way. So that this particular gene was recessive and did not carry on to the children. Next, please. Well, I was going to say by a particular date, but you know, there is no particular date I can put on when Whirlwind worked. It started working with test storage in '49. It had storage tubes in it and one row working with some density in 50. It really wasn't all working until about 51. So it's not a thing where you put it all together and you turn it on and yes, it works, or no, it doesn't work. It sort of worked gradually more and more over a period of time. But this is the control room as of about 1951. That's Jack Gilmore. That's Sam Thompson, our first computer operator. And even the control room, you can see, is quite large. This isn't the computer at all. That was the marginal checking thing. These are indicator lights. That's a synchroscope, which could be connected to probes that were scattered throughout the room that could be set where you wanted. This is an input tape reader, output scope, and so on. This control room kept changing all the time. In fact, one could almost make a history of Whirlwind by having a sequence, might even make a motion picture of the control room as it changed over the years. Now, as a secondary storage device, add the next one, please. We were first planning to use the Eastman Kodak Photoelectric reader recorder, which most of you probably haven't heard of, and those that have forgotten. And I've tried to forget it, but somebody gave me this, and I thought I'd show it to you. This wasn't one of our, well, we didn't really think this up. It really wasn't one of our better ideas either. It had two problems. One is that you wrote on it, and then you had to take it off and develop it before you could read it back. And secondly, it had registration problems. Very hard to write on one machine and then read on another. So, although we did make it work after a fashion, we gave it up. We used, the primary input to the machine for a long time was punch paper tape. Next, please. This, you've seen several of these already. This is a tape verifier station. We used a Ferranti photoelectric tape reader for the input. Then we went to magnetic tape devices. Next, please. These tape transports were built by Raytheon. They were 6 bits wide. There are 5 of them. We had the same problems everybody else did. The tape had blemishes in it, the forms of dust or something, which would push the tape away from the head as it went by, and you get a dropout. So after a while, we persuaded ourselves that the trouble was all dropouts, and we never knew a case of an extra bit appearing. So then we said, well, perhaps these dropouts aren't very wide on the tape. So we ran them, and it turned out, in fact, they weren't. So we ended up ganging the 6 channels into 3 groups of 2 each, spread half across the tape, one of which was used for timing, and 2 of which were used for data. And under these circumstances, it worked very well. Incidentally, to show you what you can do if you haven't got much storage, we wrote a test program for the machine to look into this. This test program ran the tape unit, wrote blocks of 128 lines, all ones, in blocks, numbered blocks. It then went back and read it block by block, checked it. If it was all ones, it went on. If there was a 0 someplace, it stopped, and it punched out on paper tape the number of the block and a tape image, that is an image on the paper tape, which was also 6 wide, of what the sequence of 0s and 1s in that block looked like. And this was all done in 32 16-bit words, and it shows you what you can do when you have to. Now the special tubes, the tubes that were used for memory were some special tubes built at the laboratory. Next, please. Well, we missed it, but it's just as well, probably. It was a cross-section. I wasn't going to explain it anyway. But it was a special tube. This is one on the trolley being pumped down. This is a flood gun. This is the read-write gun. There was a mica surface here. We made them work, although I aged a great deal in the process. They were designed for 10 or 32 by 32 array on the face of on the mica. And we started out and got 256 and gradually built it up over a period of time. Next, please. Oh, incidentally, I forgot to say that if I could go back one, it looks like we're having problems with the machinery. That's Jay, of course. That's Steve Dodd, who is the chief storage tube engineer, and that's Pat Utes, who is in charge of the tube shop. Next, please. That's the storage tube row. That's one of the digits. And there were 2 of these tubes, and each one was put in a box and trimmed up to look alike, and you can replace the tube by replacing the whole box. These are drivers and amplifiers and so on that went with it. Now, I've said very little about contractual and funding matters while all this was going on. Interest in the analyzer had dwindled and finally disappeared completely. The Special Devices Center had disappeared also, and the Whirlwind project was supported by the Office of Naval Research. The interests of the Digital Computer Laboratory were primarily in control applications. such things as fire control, tracking aircraft, anti-sub warfare, simulation, air traffic control, and things of that sort. A number of pioneering reports in these areas were written about 1947 and on. In 1948, we had some support to look into the application of digital computers to air traffic control. There was no formal military interest in these matters, however, and the Office of Naval Research was primarily interested in mathematical applications, and they were concerned about the amount of money we spent. We were spending about $1 million a year, which was a large fraction of ONR's budget, and this created a considerable problem. And I won't go into it here because there is a good book on the subject written by Tom Smith and Kent Redmond, which unfortunately has not been published, but a number of manuscript copies are available, and it talks about and goes into this in considerable detail. By roughly the beginning of 1950, the machine was working, and the Navy decided that the time for putting in $1 million a year had gone by, and although they were willing to continue to support it and to support some of the applications, there was a considerable crisis. It turned out, however, as so often happens apparently, that at this very critical juncture, an optimum application appeared, one that fitted Whirlwind and that Whirlwind fitted, or that fitted the thinking behind Whirlwind. It needed Whirlwind and had a high priority with all that that entailed in the way of money and support, and that application was air defense. It was about this time that the Russians had developed atomic weapons and intercontinental aircraft, and considerable attention was being given to air defenses. Some of the problems were low-flying aircraft, the problem of mini radars covering large areas, and so on. And George Valley at the Institute was concerned with this, was introduced to Jay, and it turned out that what he needed was a digital computer, and what we needed was air defense. So the Air Force support appeared in the nick of time, and we began to work a large part of our effort on this particular problem. Next, please. That's rather hard to see, but it's the best one I could find. That's a picture of the MEW, Microwave Early Warning Radar. I think it's the one at Hanscom. It's hard to tell. The MEW is long gone, and the hill on which it sat is long gone. But that was the first radar to be hooked up to a computer. It turned out there was a group at the Cambridge Research Center which was working on means for transmitting radar data over telephone lines. So we took that radar and their telephone line transmitters and hooked it up to Whirlwind and started tracking aircraft. Now, in 1951, all this activity led to a decision to go ahead and develop a system of this sort for operational use. It led to the formation of the Lincoln Laboratory, and the Digital Computer Laboratory became one of the divisions of the Lincoln Laboratory with responsibility for the design of SAGE. The Digital Computer Lab did continue, and using primarily Navy money, carried out a program of computer applications and made the machine available to many people around MIT for many purposes. We put our attention in two things. One is additions to Whirlwind, to use it as a real-time control machine and to build the rest of the facilities that were required. And the other was to begin the design of the new machine for SAGE. Next, please. One of the things that we did, and I think we did first, although I'm being very cautious about it after the last 2 days, is we were the first people to hook a display onto a computer. This is one of the standard Whirlwind displays. It consisted of a large scope. We put some digital analog converters on 2 of the flip-flop storage registers. So when the machine wanted to put a spot on the scope, it would put the right XY positions into these registers and then would order an intensification pulse, and it would put a spot on the scope in the place that's determined by the machine. Next, please. Whoops. Well, that's half of it. Oops, okay. I don't know how well you can see this, but these are some dots. This represents, in fact, some radar data. There's a target, there's the fighter, and here's some digital information, which at this time was done by just showing the character by spelling it out in dots. We went ahead to build character generators, vector generators, and so on for the purposes of the air defense operation. It all worked in series. No matter how many of these you had, the same deflection voltages went to all of them, and then the computer decided which scope it wanted to intensify, so we could put different pictures on different scopes. Next, please. This is a light gun, which was developed for as an input device. This is the thing in its can. This is one of the early ones, this little spout. You put the spout over the place where you expected the spot to arrive. When the computer intensified that spot, it was picked up by this photo tube, sent back to the machine, and the machine had said, oh, that one. And then it did what you had told it to do by setting other switches. Now, in order to get on with the what came to be known as the Cape Cod system, which is the breadboard or brass board for SAGE, there were a lot of other problems that had to be solved. And particularly, we needed some drum storage. Two kinds of drums. Next, please. One of them was just for auxiliary memory, because the program for the Cape Cod system actually ran 20,000 instructions. We only had 2,000 in core. And the other was a buffer drum, so that all the radar data and other kinds of data that kept pouring in, we didn't have a good interrupt system, nor did we have really time to handle it on an interrupt basis. It was stored on a buffer drum with marker channels, and then the computer could go read a section of it when it chose. We bought these drums from ERA. This shows one on this side. I don't know which one is which, but this is one on this side and this is one on the other. Next, please. This is some of the telephone line terminal equipment, not only from telephone lines, but from many other things. There were just thousands of switches and dozens of phone lines that came in. In fact, I remember one of our fellow sister organizations who was working in air defense came around to visit us one day, and how shocked they were to find out our telephone bill was larger than their total budget. Next, please. This shows a Cape Cod display as it finally came about. This is the large scope, which I mentioned, computer-driven. This is a small one for digital information. These are some of the buttons that the operator would push to tell the machine what to do, and he's holding a second-generation light gun, but basically the same sort of thing. Next, please. This is one of the control rooms, about 1954. It's, once again, a hard thing to get a good picture of. This is one of the officers. He's got two assistants with him, and he's looking at the aircraft, deciding what to do. This is a weapons control room, and then these people do various things as he's told to. If you look back here, that little thing sticking up there is a photocell, which is over one of these displays, which is in a horizontal position, and which was used for masking or to give the computer particular kinds of information. I told Bob Weezer, who built this, that it looked to me like a warehouse that somebody had just left some scopes scattered around in, and I don't think he ever forgave me for it. There were about 20,000 instructions, as I said, and we had to do quite a lot of work in developing means for writing programs of that sort and keeping track of them. There was a lot of pressure on space. The size of the operation was going up. During the time when the Whirlwind was built, it was a large operation by the standards of the early days of the computer business. There were about 60 to 70 members of the technical staff in the organization, and of the order of 175 people altogether. And this began to go up substantially, as you can imagine, when we started getting into things of this sort. Now, so we moved some of the people over to the Whittemore building and began to work on the SAGE machine. And the first thing we knew was we had to do something about those storage tubes. And the laboratory had been working on Jay Forrester's core memory for some time, and it seemed to show the promise for getting the reliability and speed that we needed. So we immediately began working on that. Next, please. That's a wound ribbon core, 16 by 16. At the time in 1952, when this was taken, the ceramic cores, we could not get the right characteristics and the right consistency. So we began working in parallel on this kind of a thing. I think we could have made one out of wall-driven cores, but it would have been a lot slower and less reliable. Next. This is one of the first core planes. This is a ceramic core, 16 by 16. These cores came from General Ceramics, and lo and behold, about the summer of '52, we began to get cores that we could actually use. Next. We decided to build one. This is a 32 by 32 core plane from the first core memory. Next, please. This is the first core memory here. This is the memory test computer, which we built as a test instrument for checking out the core memory. It has two reasons for being famous. One is the first computer to have a core memory, and the other is the first computer that Ken Olsen ever built. As probably most of you probably know, Ken Olsen is the president of the Digital Equipment Company, and he makes computers by the thousands, but that's his first computer. After it did its work on the core memory, we used it as a test device. It tested all of the SAGE peripherals, and it also was used for data reduction. This worked so well that we decided to put it into Whirlwind. Next, please. We built a second stack and installed it in Whirlwind. Here it is. This is one stack, the other stack. You can see the core planes in the middle here. And this is the associated electronics. It had a tremendous effect on Whirlwind. It approximately doubled the operating speed. It quadrupled the input data rate. The maintenance on the storage row went from 4 hours a day to 2 hours a week. The mean time to failure on the machine on the memory went from 2 hours to 2 weeks. And Pat Utz's entire tube shop was freed up to work on the display tubes. We then built a 4K memory for MTC and subsequently another 4K memory for Whirlwind. And subsequently built transistorized memories and ultimately a 65,000 word memory, which went on TX2. Next, please. This shows a map of the Cape Cod system in its heyday with the locations of the radars. We had two big radars out here on Cape Cod, and another one in Montauk, and one of them up here in Brunswick. The rest of them were small radars. And these things were all hooked together and were run by Whirlwind. We ran demonstrations about once a week in which we used SAC aircraft. We had a lot of backing in those days. SAC aircraft came in to be targets, and the fighter aircraft from Air Defense Command were scrambled against them, and general officers came and watched it work. And it really worked. You know, Whirlwind had a character all its own. When there wasn't anything important going on, it could be very difficult. But if you rushed out and said, hey, it's time for the demonstration and General Lippisch is here, it would pull itself together and work. In particular, George Valley, I mentioned earlier, who was assistant director of the laboratory, that Whirlwind liked George. Why, I don't know. But when George was around, it just worked so good. So we always try to get him to come for important demonstrations. Next, please. I don't know whether you can read this or not. One thing I did was I said I will resist the temptation to remake any of the slides. These are all from the old Whirlwind records, 20 or 25 years old. This is a list of what Whirlwind was like at the time of the Cape Cod demonstrations. It shows the speeds and capacities and so on of the machine. Next, please. This shows the approximate, roughly the operating capability also during the Cape Cod days, about 1953 to 54. The size of the system and its operating rates and whatnot. I mean, availability rates. During this time, the machine was used for many other purposes, as I said, mathematical and experimental at MIT. It was the machine that Lanning and Zeeler used for their first algebraic compilers. We did quite a lot of work on air traffic control with the machine. Next, please. One of the things we did with it was it was the machine that computed the tapes for the first digitally controlled milling machine, which was built at MIT, which is shown there, which Forrester holds one of the patents. Next, please. This is the control room in 1959, just before it was shut down. I don't know if you can see it, but that's a hand grenade. I hope it wasn't full of something. Hanging up here in a statement that the pin would be pulled on June 30th, 1959. This is what the control room looked like at the end. By this time, we'd gotten all the engineers off the machine, but it was run by the technicians. It ran very well, but it cost about $300,000 a year to keep it going, plus the fact that maintaining the software and support software and so on was quite expensive. So we decided we'd shut it down. We expected that would be the end of it. But one of the fellows from Whirlwind, Bill Wolf, had a company, a software company. He decided he wanted the machine, and he rented it from the Navy for $1 a year. And he actually took it out of the BARDA building and moved it out to West Concord and set it up again and made it work, somewhat to our surprise. And he ran it for some years. I think the thing he wanted was not so much the central machine as all of the terminal equipment that came with it. There was an agreement between the Navy and the Smithsonian that when the Navy needed the machine no longer, it would be turned over to the Smithsonian. Finally, the Navy got tired of keeping it on its books and decided that they would abandon it to Wolf with the proviso that he had to deliver the appropriate parts to the Smithsonian. And this argument went on and on and on for a long, long time. And eventually, a couple of years ago, Ken Olson called me up and told me that Bill Wolf had called him and said he was scrapping Whirlwind and if he wanted any parts to give him a call. So Ken went over there and with some of his summer students and some trailers and collected all the parts. And I tried to get hold of the Smithsonian, and that didn't work very well. But Ken got the machine. He kept it in the trailers for a while. He then kept it in a warehouse, and eventually we got some of it out, made a display, which is now in the Smithsonian. I have two further slides, the only new ones. Next, please. This is the Whirlwind display in the lobby of the Miter Corporation. This is our farewell to Whirlwind party. And these are some of the old Whirlwind hands, gotten a little older. There's Jay, there's George Valley, and there are others scattered throughout it. And we all enjoyed the party so much we had another one in Washington. This is hello to Whirlwind at the Smithsonian. This is as it is there. You can see some of the things. What we did was we took one column out of the machine, and there's a picture behind it to show how the rest of it looks. That's the core memory. There's a drum and a number of other things. Lights, please. I'd like to make a couple of other remarks, if I've allowed the time. One of them is that Whirlwind is probably the most documented of the early computers. There's not very much published about it, but for internal reasons, there was a great deal of documentation. For instance, all the staff were required to write a biweekly report. Every other Friday, at the end of the day, you had to stop what you were doing and write a short report on what you'd done in the previous 2 weeks. And these were all put together and issued as an internal communications means. And there are literally thousands of reports, computation books, and so on. And all this information has been turned over to the Smithsonian for their archives, and it is available there. There is a Redmond Smith book I mentioned. There is a complete MITRE. There is a complete photographic archive at MITRE. We will be glad to help anybody who's trying to find out something about Whirlwind. In fact, it's kind of hard to get Whirlwind people to stop talking about it. I could say something about Whirlwind contributions. There were many firsts, stemming, I think, mainly from the fact that we were the first people to build a machine for real-time applications. We were the first people to face those problems and the first people to solve them. I'm going to be cautious about listing those, although if you will go by and look at Whirlwind in the Smithsonian, you'll see a list which has had some clearance. The second thing is that there are really two results from Whirlwind. One of them, which is more clearly known, is it's the predecessor of SAGE, which in turn is the predecessor of many of the military C-cube systems, the air traffic control system, and other large computer-based systems. Another derivative, which is less well known, is the mini-computer. Ken Olsen says that Whirlwind is the first mini-computer. Now that sounds kind of strange, because it actually was the largest of the early machines. But in architecture, in intent, in order, in structure, and in use, and so on, it is in fact a mini-computer. And the mini-computers today are much more like Whirlwind than they are like some of the other early machines. So if you all be quiet and listen, you can hear a faint rustle. And that's the millions of Whirlwind's children that are coming along in the form of chips. They're going to invade our houses. They're going to invade our automobiles. And just like Whirlwind, they're going to be smart and reliable and fun to be with. Thank you.
Thank you very much. We are running rather late. We should start again at 10 after 4. Perhaps we can have a couple of questions, urgent questions. Dr. Mulcahy?
First, I want to enter another contender maybe for the first real-time computer. It never did what it might have been asked to do. That's the Binac, made for Northrop, which actually had the inputs and outputs to accept input information, which would then be calculated on, and then output working navigation devices, presumably, and a flying missile of some sort. The second comment that I have, I may put a date on that, of course, that the Binac was demonstrated in 1949, and so I don't know how that interacts with what you consider the dates for the Whirlwind as a real-time computer interacting with something which itself was not a computer. Well, the second remark is simply that perhaps the Whirlwind was more of a Neumann machine than either the EDVAC or the Binac. For this reason, as you have related, of course, the original objective was to be satisfied, they thought, by an analog assemblage. And I remember distinctly the occasion, although I don't remember the time right now, when I and Eckert and Captain Goldstein and perhaps Chris Brainerd all were trailing up to one of those trade schools for some purpose, but as a byproduct of that purpose. We were trailing with a certain John von Neumann, who took the time and eloquently tried to persuade Brown, I believe, that you'd never get anywhere doing these things analog. You'd better convert to digital. That was the only way to go. And he was very persuasive, very elegant. And it was only a few months after that at the Naval Ordnance Laboratory, where I happened to be consulting some, there were study parties from Whirlwind, I believe, who were surveying to see whether maybe they should go digital.
Last question.
Brainerd, Moore School. I'd like to keep this on a light vein, so I'll say very quietly that I stick to what I said about MIT not having a receptive atmosphere in spring of '43 for digital computation. And the speaker mentioned Gordon Brown and such people. I knew them very well. I took into account not only Sam Caldwell when I said that, but many, many others that I knew up there. Now, my second point is this, that any history of Whirlwind should be accomplished by a study of how lucky MIT was to have it. when these other problems came along. And this leads me into my third point, that there's another computer, not much known and really not reported. Our people just got tired. There was a UDOFT, and it came in this way, and it was relayed to Whirlwind by the fact that the Special Devices Center, Admiral de Flores, gave out 2 contracts at once for a digital flight trainer. And the UDOF, the Universal Digital Operating Flight Trainer, is the one that was picked, and meanwhile, Whirlwind was going on to other things. Now, unfortunately for us, we had to deliver the whole thing to the Special Devices Center, so we had nothing left, whereas MIT had the Whirlwind left.
I'd like to say to Dr. Brainerd and to John Walkley that I certainly recognize the debt we all owe to the Moore School and the ENIAC and Johnny von Neumann and all those people. I furthermore think there's enough glory in the early days of the computer for everybody.